Hello everyone, welcome to Numerical Physics Prep. In today's lecture, we will derive the rotational equation of motion step by step, exploring how angular quantities mirror the linear ones. By the end, I will also connect this result back to linear motions, so you can clearly see the parallel between the two. So let's get started. Equation of rotational motion. First one is angular velocity attained by rotating bodies after time t. So our equation is omega equal to omega naught plus alpha t. Here omega is final velocity, omega is final velocity, omega naught is initial velocity, and alpha is angular acceleration. Alpha is angular acceleration and t is time. So this is our equation, omega equal to omega naught plus alpha t. So consider a rigid body. Consider a rigid body about fixed axis with constant angular acceleration that is alpha. Then we know alpha equal to d omega upon dt because angular acceleration is equal to rate of change of angular velocity. Then alpha is equal to d omega upon dt. Then cross multiply alpha dt equal to d omega, which is equation first. Then integrating equation equation within limits that is when time equal to 0, omega is omega naught, which is initial velocity, and when time equal to t, omega is omega, which is final velocity. Then put this in equation first, we get integrating alpha dt, limits is 0 to t equal to integrating d omega, limit is omega naught to omega, then alpha is constant, then 0 to t dt equal to d omega, limits is omega naught to omega, then integration of dt is t, which I tell in last video, and similarly d omega is omega, limit is omega naught to omega. Then putting limits, we get alpha t equal to omega minus omega naught. Then this implies omega equal to omega naught plus alpha t, which is our first equation of rotational motion. Then second is angular displacement of the body rotating with constant angular acceleration. So equation is theta equal to omega naught t plus half alpha t square. Here theta is angular displacement. and omega naught is initial velocity and alpha is angular acceleration and t is time. Then derive this equation. Let the angular velocity of body at any instant of time t is omega, then omega equal to d theta upon dt, because angular velocity equal to rate of change of angular displacement. Then cross multiply, we get omega dt equal to d theta, which is our equation first. Then we know omega equal to omega naught plus alpha t, which is equation second. Put second in first, within limits, and integrating, we get omega is omega naught plus alpha t dt equal to d theta, and limits is 0 to t for time, and displacement is 0 to theta. Means when time equal to 0, displacement is 0. When time equal to t, displacement is theta. Then integrating, we get omega naught t plus alpha t square upon 2 equal to d theta is theta. Okay, I hope you understand this step. Otherwise, I also derive in detail, that is multiply dt in equation, or we say that open the brackets, we get 0 to t omega dt plus integrating 0 to t alpha t dt equal to integrating d theta, which is 0 to theta. Then apply the integration formula. Omega is constant, sorry, here is omega naught. Omega naught is constant. We get integration of dt is t, which is limit 0 to t, plus alpha is constant, and integration of t dt is t square upon 2, limit is 0 to t, and integration of theta d theta is theta, limit is 0 to theta. Then putting limits, we get 0 t minus 0 plus alpha upon 2 t square minus 0 equal to theta minus 0. Then solving equation, we get omega t plus alpha upon 2 t square equal to theta, which is our second equation. Theta equal to omega naught t plus half alpha t square. Then third one is angular velocity attained by a body after covering angular displacement. So here equation is omega square minus omega naught square equal to 2 alpha theta. This is our equation. Then for deriving, let dw be the change in angular velocity of body in time dt, then alpha equal to d omega upon dt. This is equation first, then multiply and divide equation first by d theta on right side. We get alpha d omega upon dt multiply d theta upon d theta, then alpha equal to omega upon d theta, because omega equal to d theta upon dt. Then cross multiplying equation, we get alpha d theta equal to omega d omega, which is our equation second. Then integrating equation we get integrating within limits is when time equal to 0, angular displacement is 0, and velocity is omega naught. When time equal to t, theta equal to theta, and omega is omega. Then putting limits, we get integrating alpha d theta, limit is 0 to theta, equal to integrating omega d omega, limit is omega naught to omega, then alpha is constant, 0 to theta d theta, equal to integrating omega d omega, then omega naught to omega, then integrating d theta is theta, limit is 0 to theta, equal to here integrating of omega d omega is omega square upon 2, limit is omega naught to omega, then alpha theta minus 0 equal to 1 upon 2 omega square minus omega naught square. Then arranging this equation, we get 2 alpha theta equal to omega square minus omega naught square, which is our third equation. So these are the equation which is same as linear motion, only the variable changes. So let's compare this linear and rotational motion equation. So here in linear motion, first equation is v equal to u plus at. Here v is final velocity, u is initial velocity, and a is linear acceleration. But in rotational motion, omega is final velocity, omega naught is initial velocity, initial angular velocity, and alpha is angular acceleration. And second one is s is linear displacement, and in rotational motion, theta is angular displacement. So these are the comparison which is more important when we shift the system from linear to rotational motion. Thank you for watching. If you like the video, please subscribe, like, share, and hit the bell icon to getting the valuable videos. Thank you.